F N. Okay, we start the class today. So the last class in the physical chemistry one, we just started how the polarity of the molecules arises. And today we are going to discuss how the hydrogen bonding is formed. I'm going to show you two slides. Now look here. Now look here. Dipole moment is the magnitude of charge multiplied by the distance between the charges. I have already told you, when two atoms with different electronegativities combine, electronegativity is the capacity of an atom to attract the shared pair of electrons towards itself, and is anybody waiting in the classroom? Just I wanted to check. Screening mode. Okay, only 40 have come. Nobody is waiting, no? Right. Okay, look here. So the polar bond is formed when atoms of different electronegativities combine. So electronegativity is the capacity of an atom to attract the shared pair of electrons towards itself. Therefore, assuming a complete transfer of electron, we are taking the charge as 1.602 into 10 power minus 19 coulomb. This is the magnitude of the charge. In the case of hydrogen chloride, it is assumed that the hydrogen possesses a +1 positive charge, and the chlorine possesses a -1 negative charge. Therefore, we are assuming that there is a complete transfer of electron from hydrogen to chlorine. If that is the situation, now the charge is 1.602 into 10 power minus 19 coulomb. Coulomb is the unit of a charge. So it is 1.602 into 10 power minus 19 coulomb is the unit charge. Now the bond length for hydrogen and chlorine bond is 1.275 into 10 power minus 10 meter. Therefore, the dipole moment is the magnitude of charge multiplied by the distance between the charges. Therefore, in this case, I am multiplying the magnitude of the charge, that is 1.602 into 10 power minus 19 coulomb, multiplied by 1.275 into 10 power minus 10 meter. This is the bond length. Bond length is the distance between the hydrogen nucleus and the chlorine nucleus. Therefore, that itself is taken as the separating distance between the two charges. Therefore, when you multiply this, you are getting 2.0.42 into 10 power minus 30 meter coulomb. So the meter coulomb is the unit for dipole moment. So watch closely what we have done. We have assumed a complete transfer of electron from hydrogen to the chlorine. Therefore, we are assuming unit charge. One unit charge is 1.602 into 10 power minus 19 coulomb. Now the bond length is taken as the distance between the hydrogen and the chlorine, and consequently it is taken as the distance between the plus charge and the minus charge. Therefore, I am multiplying this with 1.275 into 10 power minus 10 meter, which is the bond length. So when I multiply, I am getting the value to 20.42 into 10 power minus 30 meter coulomb. Therefore, the meter coulomb is the unit for dipole moment. So normally dipole moment is given the unit d by. D by is the name of the scientist. Therefore, it is given the unit d by 1 d by 1 d by is equal to 3.338 into 10 power minus 30 meter coulomb. Therefore, I want to find out the dipole moment in terms of d by. Therefore, mu is equal to 20.42 into 10 power minus 30 divided by 3.338 into 10 power minus 30. So when you do this division, you are getting 6.12 d by. So this 6.12 d5 is really a very high quantity, but the actual value of the dipole moment of hydrogen chloride is 1.03 d by. Why there is a vast difference between the experimental value and the calculated value? This is what we have to understand. Actual research is this. We are doing something and we propose some idea. What we theoretically find out, whether it is in agreement with the experimental observations. Whenever there is a discrepancy between the theory proposed and the experimental observations, the correct explanation which is given for this discrepancy will result in a new finding. So this is how new findings are coming in chemistry and in other fields of the sciences. Therefore, here there is a discrepancy. You can very well understand the fundamental explanation or the basic explanation for the dipole moment is all right. It is the magnitude of charge multiplied by the distance. There is nothing wrong in this definition. It is the correct definition for dipole moment. But when you do the calculation for a molecule, we have taken the hydrogen chloride molecule to do the calculation, and two things we have assumed. One thing is there is a complete transfer of electron. Therefore, I am assuming that hydrogen is having 1 plus charge and chlorine is having 1 minus charge. This is one assumption for this calculation. And the second assumption is the charges are separated for a distance of the bond length. So this separation is another assumption. Having these two assumptions, I am calculating the dipole moment and I am getting the answer 6.12 d. That 6.12 d is a very high value. Therefore, the experimental value is 1.03 d. Therefore, from this discrepancy, we are coming to an understanding that there is no complete transfer of electron. So, the error supposed to be in the two assumptions what we have made. What is the first assumption? There is a complete transfer of electron. That means the electron density is completely shifted from hydrogen atom to the chlorine atom. So that assumption is wrong. Or the next assumption which can be wrong is the bond length is not the distance of a separation between the two charges. Therefore, these two errors can be present only in these two ideas. Therefore, we are coming to a conclusion that hydrogen chloride molecule is not purely ionic, it is mostly covalent. So what is an ionic bond? Ionic bond formation is taking place when there is a complete transfer of electron from one atom to the other atom. Whereas a covalent bond formation is taking place when there is a sharing of electron between the two atoms. Therefore, in order to form the bond between the hydrogen and the chlorine, hydrogen has donated one electron and the chlorine has also donated one electron. There is no complete transfer. Actually, sharing of electron has taken place. Therefore, while the electrons are shared, I have already told you, it is because of the difference in the electronegativity. Chlorine is found to be more electronegative than hydrogen. Therefore, the chlorine is trying to pull the shared pair of electrons towards itself. Therefore, the electron density is not at the middle. If the electron density is at the middle, what would have taken place? The charge may be 1.602 into 10 power minus 19, but the distance between charges will be 0. So in such cases, you will be getting zero dipole moment because the charges are not separated. Charges are there. It is exactly at the middle. Therefore, even hydrogen would have not possessed the partial positive charge, or chlorine would have not possessed a partial negative charge. Now, because of the difference in the electronegativity, the charges are slightly shifted towards the chlorine. Even then, there is no complete transfer. If a complete transfer is there, then it will become an ionic bond. If the dipole moment is higher than 1.03 dBi, then more ionic character is assumed. Therefore, as far as the present calculation and the experimental observation are concerned, the hydrogen chloride molecule is found to be more covalent than ionic. So the charge is not completely separated to the distance of bond length. Therefore, there is only a partial separation. The charge separation is a totally partial. That is why we are not able to say that hydrogen is possessing a unit positive charge and chlorine is possessing a unit negative charge, whereas we can say that hydrogen is possessing a partial positive charge delta plus and chlorine is possessing a partial negative charge delta minus. So this is how the dipole moment has risen. So in this molecule, hydrogen and chlorine, they are not separated. Suppose if you dissolve an ionic compound in water, what will happen? Automatically, the ions will be separated due to the dielectric constant of the water. So polar solvents will always try to separate the ions. Therefore, what will happen? H plus will go one side and Cl minus will go on the other side. But in this case, there is no complete separation of hydrogen and chlorine. Therefore, they are existing in a bond. They are connected. But at the same time, they are not of zero charge. A partial positive charge is imputed on hydrogen and a partial negative charge is imputed on chlorine. Therefore, the hydrogen chloride molecule is mostly covalent and it is less ionic. So in postgraduate classes, when you come to MSc, you will be studying the partial ionic character and the derivation of a bond-length equation to find out the partial ionic character present in a molecule. So this involves so many calculations. But at present, you have to understand what is a dipole moment. So you should always remember the dipole moment is equal to the magnitude of a charge multiplied by the distance of separation between the charges. So in the case of hydrogen chloride, we have seen the calculation and we have calculated the dipole moment, and the theoretical dipole moment comes about 6.12 dBi and the experimental value is 1.03 dBi. There is a vast difference, and this difference is due to the covalent nature assumed by the molecule. Therefore, hydrogen chloride molecule is mostly covalent and it is less ionic. So there is a partial separation of the charges between the hydrogen and the chlorine. Therefore, the hydrogen possesses a partial positive charge and the chlorine possesses a partial negative charge. Anybody has a doubt in this? If there is no doubt, I can pass on to the next idea. So this What we have explained earlier, it is in the case of a diatomic molecule. What is a diatomic molecule? You should understand what is atomicity of a molecule. Number of atoms present in the molecule is called atomicity of the molecule. Diatomic molecule means the molecule contains only 2 atoms. The atomicity of oxygen molecule is 2. Atomicity of ozone molecule is 3. Atomicity of methane molecule is 5. Atomicity of ammonia molecule is 4. So in the case of multi-atomic molecules, so the discussion, what we have seen earlier, the magnitude of the charge multiplied by the distance of separation of the charges. This calculation can be easily done for a diatomic molecule. But in the case of multi-atomic molecules, you may very well calculate the bond polarity, but the dipole moment shown by the entire molecule depends upon very many factors. Your bond may be polar, but you cannot expect the molecule as a whole behave as a polar molecule. That is why multi-atomic molecules are given a special attention. Actually, it is here the symmetry of the molecules plays a vital role. Actually, the dipole moment can be approached in terms of group theory also. Group theory also plays an important role in determining the dipole moment of the molecule. And I will be discussing this when we discuss the group theory in detail. So multi-atomic molecules, sometimes they are polar, sometimes they are non-polar. Somebody is talking. Please mute. I don't know who is talking. Please mute yourself. Jency? So 41 participants have come, only 38 messages I have received. Please, those who have not sent your register number and name, please do it, because you have to be given the attendance. Please do it. Later on, you do not tell me that you have not given the attendance. In order to mark present, every one of you should type your register number and name and put in the chat box. Do not repeat, just once you do, and then do not share any of your private things, and you just type your register number and name. Okay, right. While during the classes, you do not unmute your mic, because sometimes a noise, I'm able to listen to noises. Therefore, do not unmute. Keep yourself muted and listen to the class carefully. Now again, I would like to present the screen. Look here. So in the case of multi-atomic molecules, sometimes they are polar and sometimes they are non-polar. So whether it is a polar or non-polar, that depends upon 3 important factors. The first factor is the arrangement of atoms. And the second factor is the bond length. And the third factor is the bond angle. So look here. First, I would like to take the carbon dioxide molecule. So carbon dioxide molecule, carbon is at the center. On one side we have oxygen, and on the other side we have oxygen. And we know that the oxygen is found to be more electronegative. Oxygen is found to be more electronegative than carbon. Therefore, the shared pair of electrons between the carbon and the oxygen are attracted more towards oxygen. Therefore, the electron density is shifted towards oxygen. Therefore, this oxygen possesses a partial negative charge, and the carbon possesses a partial positive charge. And this oxygen also possesses a partial negative charge. Therefore, if you want to find out the dipole moment of the carbon oxygen bond, you can very well do that. It is the charge multiplied by the distance of separation, and this side also it is the charge multiplied by the distance of separation. But actually the center of a positive charge is here, and the center of the negative charge is also falling on the same point because of the vectorial sum, because the dipole moment is a vector. So when you take the vectorial sum, the center of the positive charge falls over here, and the center of the negative charge is also falling over here. The zero dipole moment of a carbon dioxide molecule can be explained in two different ideas. Number one vector is pulling in this direction and the other vector is pulling in this direction. Therefore, the vectorial sum of the dipole moment becomes zero. And the second idea is the center of the positive charge and the center of the negative charge, they fall on the same point. Therefore, the distance between the charges becomes zero. Therefore, the magnitude of the charge multiplied by the distance zero, again you will be getting the mu zero. So that is how the carbon dioxide molecule is not having a permanent dipole moment. So carbon dioxide molecule has polar bonds, but as a whole the molecule is not a polar. It is the same with the carbon disulfide molecule. You look at the carbon disulfide molecule. Carbon disulfide molecule has a carbon, double bond, sulfur, and on the other side also a double bonded sulfur. Therefore, here also sulfur is found to be more electronegative than carbon. Therefore, sulfur assumes a partial negative charge and carbon assumes a partial positive charge, and this sulfur also assumes a partial negative charge. As it was discussed in the case of carbon dioxide, the vectorial sum of these two vectors, the carbon sulfur bond has a polarity, and this carbon sulfur bond also has a polarity. So when you vectorially sum these two polar vectors, you will be getting the dipole moment is zero. Or you can explain in a different term, the center of the positive charge is here and the center of the negative charge is also on the same point. Therefore, as per our theoretical explanation, the dipole moment mu is equal to the charge multiplied by the distance of separation between the charges. As the center of the charges fall on the same point, that will become zero. Therefore, dipole moment becomes zero. Therefore, in both the ways, the zero dipole moment of carbon dioxide and the carbon disulfide can be explained. But if you take the water molecule, the actual structure is this. The oxygen in water molecule involves sp3 hybridization. And we all very well know that sp3 hybridization will lead to tetrahedral structure. sp3 hybridization will lead to tetrahedral structure. In the case of tetrahedron, actually the two corners of tetrahedron are occupied by hydrogen atoms. The other two corners are occupied by lone pairs. So these lone pairs, which are present in two corners of the tetrahedron, they will repel the bond pair. What is a bond pair? They are the pair of electrons involved in the bond formation. What are lone pairs? The pair of electrons which are not involved in the bond formation. Therefore, here between the oxygen and the hydrogen, there are two electrons. Even these two electrons, one electron is shared by hydrogen and one electron is shared by oxygen. Therefore, this is a covalent bond. And on the other side also the same. One electron is shared by oxygen and the one electron is shared by hydrogen. But these two electrons are supposed to be at the middle of the bond. But because of the high electronegativity of oxygen, the electron density is shifted towards oxygen. But all these things are happening. And apart from this, the lone pair repels the bond pair. Therefore, what happens? The bond is bent. If these two lone pairs are not there, the water molecule would be existing in a linear shape. If water is a linear, automatically what we discussed in the case of carbon dioxide and carbon disulfide will be the same explanation for the water molecule also. So these two vectors will cancel out each other and the water will not have a dipole moment. If water is not having dipole moment, water will not exist in liquid state. So all these things will lead to more complications in the existence of universe itself. But only because of these two lone pairs, because of the lone pair bond pair interaction, the water molecule is bent shaped. And because of this bend, what happens? The hydrogen possesses partial positive charge, oxygen possesses partial negative charge. One vector is slightly bent, another vector is also slightly bent. Therefore, the vectorial sum becomes here. Therefore, it possesses a dipole moment. Or you can explain like this. The center of the negative charge is here on the oxygen, but the center of the positive charge is not on the hydrogens, it is almost here. Of course, in this place, there is no atom at all. But even though there is no atom, the vectorial sum, that proves that the center of the positive charge can be assumed here. So it is only the multiplication of the charge multiplied by the distance between these 2 points because of the bent shape. So because of the bent shape, the water assumes a permanent dipole moment. And only because of this permanent dipole moment, water molecules will align themselves in such a way that the hydrogen of one molecule goes closer to oxygen of the other molecule, and then the hydrogen of the other molecule goes close to oxygen of the other molecule. This is how the water molecules aggregate themselves and they form the liquid state. Otherwise, water will be existing only in the gaseous state. As I have discussed earlier, even our adaptation, our external structure, our form, everything depends upon how the molecules are available for us. If water is existing in the gaseous state, then we will not be having this type of human structure. You might have seen the plants in the deserts. Plants which are in the deserts will be having leaves in the form of thorns in order to reduce the transpiration. Because of the environmental adaptivity, if you see the plants which are grown in the places where plenty of waters are available, they will be having leaves with a large surface area to increase the transpiration. More amount of water has to be evaporated. Therefore, it all depends upon how the water is available. So we have a mouth, we have nose, we have ears and all that just because water is existing in the form of liquid. If water exists in the form of gas, then we will be having a different organ somewhere here in the head or something like an umbrella or something, some tube-like structure to absorb the water from the air. Our structures will be different. Even human beings might be having a tail or a horn. So it all depends upon only these two lone pairs. Actually, we have to thank the two lone pairs which are present in the water, which made the OH bonds bend, and because of that, water is existing in the liquid state. And similarly, one such another example is sulfur dioxide. Sulfur dioxide molecule is also having permanent dipole moment. Actually, the sulfur dioxide molecule is also bent. So S double bond O, S double bond O, it is also bent like this. And because of the bent shape, it also has a permanent dipole moment. And you can take another example, ammonia. See, nitrogen, oxygen, sulfur, selenium, tellurium, these are all the elements in one group. Sorry, oxygen, sulfur, selenium, tellurium, polonium. So nitrogen has one lone pair. Actually, the hybridization involved in nitrogen in ammonia is also sp3, and I have already told you, nitrogen is sp3 hybridized, and this sp3 hybridized nitrogen has tetrahedral shape, but in the tetrahedral shape, nitrogen, one corner of the tetrahedron is occupied by one lone pair, whereas all the other corners are occupied by security. Somebody is annotating. Okay, right. So here one corner is occupied by the lone pair. So because of the lone pair, in the case of water molecule, two corners are occupied by the lone pair. In the case of ammonia, one corner is occupied by the lone pair. That is why ammonia is said to have pyramidal shape. And now you see, because of the lone pair bond pair interaction, again it is interacting. Because of the lone pair bond pair interaction, the bonds are bent. Therefore, this hydrogen and nitrogen bond is polar because of the difference in the electronegativity. This nitrogen-hydrogen bond is also polar. This nitrogen-hydrogen bond is also polar. But you add the vectorial sum of these polarity vectors. When you add all these polar vectors, you will be having the dipole moment in this direction. So this is the dipole moment. Therefore, ammonia is having a permanent dipole moment. And if you take a methane molecule is also sp3 hybridized, and all the four corners of the tetrahedron are occupied by hydrogen atoms. And also there is a difference between the electronegativities of carbon and hydrogen, and each bond is polar, and all that everything is true. But in this case, as all the bonds are spatially oriented, their vectorial sum becomes a zero. Similarly, in the case of a carbon tetrachloride also, all the bonds are spatially oriented in such a way that the vectorial sum of all the bonds, they become zero. Therefore, the carbon tetrachloride is non-polar. But if you take methyl chloride, this one bond alone is having a dominant dipole moment. This bond has a dominance in the dipole. Therefore, methyl chloride is found to be polar, whereas a carbon tetrachloride is found to be non-polar. and methane is found to be non-polar. Ammonia is found to be polar. Water is found to be polar. Therefore, in all these molecules of multi-atomic nature, and these molecules of multi-atomic nature, the polarity of the bond arises due to the difference in electronegativities, but the overall, the net polarity of the molecule depends upon the arrangement of atoms, the bond length, and the bond angle. Therefore, multi-atomic molecules, sometimes they may be polar, sometimes they may not be polar. But their polarity depends upon not only the electronegativity difference, but also upon the arrangement of atoms. That is the spatial orientation of atoms, or the bond length, or the bond angle. So this is how a molecule can be found out whether it has a permanent dipole moment or not. If you have any doubt, you can ask me. Students, if you have any doubt, you can unmute yourself and ask me.